All right, so there we go. Okay, so we're going to look at the equations of motion. Okay, and like I said the other day, when you want to define the motion of an object, you can always break it into two different components. One, which is the translation, plus another one, which is the rotation. Okay? Generally, the translation will be taken care of, from dynamics. I'm going to change it here, but generally, summation of force equals to MA. And the one that takes care of the rotation is summation of moments equals to I alpha, no? All right? So this is translation, this is rotation. So let's first look then at the translation. Okay, so here I just want to make a little difference. It makes really no difference, but so for the translation, equation of motion is generally obtained in engineering from Newton's second law, which is what? We just read it before. Summation of forces equals to MA. But actually, this is a simplification, okay? But the most, or the most general form of Newton's second law is based on linear momentum principle. I mean, if you try to write it, it sounds complicated. Once you write the equation, it's pretty simple. Okay, so basically, what is the most general equation? Is summation of forces, and this is the way generally you study in physics, is d dt of a variable, of a quantity called P, where P in here is the linear momentum. Okay, and P, what is momentum, is m times velocity. Okay, so for example, what is the assumption that generally is done? Let me put vectors here to show that it's a vector. So what is the assumption that generally is done in dynamics is that this is equal to d dt mv. So this is equal to dm dtv plus m dvdt. But what happened in most cases? In most cases, we have that the mass is constant. So this one is 0, okay? This term is 0. And then what is dv dt? Is the acceleration, okay? So that's why you have summation of force equals to ma. But the most general form of the summation, of the translation is really based on linear momentum. So for example, if this is some problems that you have to do, it's easier to understand. Obviously, it's easier to solve with only one of these two terms. But what happens, for example, if you need to study the motion of a space rocket? Space rockets carry fuel, no? So as you burn the fuel, the mass is going to change. So you think about it, if you needed to write down the equation of the space rocket, you will have to have this term into consideration, no? Okay? And then this term will also become a relative velocity. Better. We're not going to go into kinematics. But I want to say that be careful with these things. It's not only summation of force equals to ma. If the mass changes, you might have both terms, okay? So the real form for the translation is really based on linear momentum and not in constant acceleration. Because if you say constant acceleration, it does imply that the mass, it might imply that the mass is constant, okay, or not, all right? Depending. Okay, so let's say now that you have a general object or general body. Doesn't matter where you put the coordinate system, okay? Okay, so this is your general body. And let's say we just look at a little cube of it, okay? A little volume and a control volume of it. This will be your dV. So this body over here, in order to have motion, is going to be subjected to different forces. The different forces are going to induce on the surface a stress tensor, no? That could be normal or could be shear, depending on if it's on the direction of the normal vector or not of the surface, okay? In addition to that, this body is going to have a certain mass, okay? So let's call this, and this will be the gravitational force, will be instead of using mass, we're going to use density, because what is density? This is for unit volume. Density is mass per unit volume, no? So we just look at a unit volume. Density will be equivalent to the mass. And let's define this one now as B, okay? And we'll see what B will be in a minute, okay? So this will be, so the T over here, since I have time, will be the Cauchy stress tensor. And the rho B will just be the body forces, okay? So B could be G, all right? Okay. So now, remember statics dynamics, always the procedure is that you do a free body diagram, no? And you write down the equations for the free body diagram. So that's what we're gonna be doing now. So page 83. So applying the equation, which is the one we just had, summation of forces equal to d p dt equal to d dt and v. What are we gonna have? Okay, so on the left hand side of this equation, what do we have? Forces, no? On the right hand side, we have what is known as inertia effect, which basically inertia effect means effects due to the motion of the object. All right, if the object is not moving, what would be the inertia effect? Zero. Okay, that's what is statics. Okay, so what is this things? What are the forces? We know we can have forces that will be in function of the stresses. So we can write these ones. We know stresses are defined on surfaces. So we can say T of IN on the surface. This would be external forces, if you want, no? Action of the external forces, but we write them down in function of stresses. Plus now you can have the effects of the body forces, the mass of the object, okay? And this one is based on the volume. So this one is surface, this one is volume. And this one is rho. I call it B sub I because you might have effects on the X, Y, and Z, no? G1, G2, G3 don't have to be just in one direction, dV. And now this will be equal to what? D dt of the mass, which is mass, which we describe as a function of density, which is mass over volume, so will be related to the volume. We have density. Now, times the velocity, can be one or two direction, and this should be related to the volume. Okay? Okay, so obviously this is the more general form, but we're going to simplify it. Okay? So let's say here, recalling the Cauchy stress formula, which basically is what? Ti of n vector is equal to the second order stress tensor sigma ij times whatever direction you have nj. Okay? And initially, and assuming static condition, which means what? V sub I equal to 0. Okay, so basically what I'm doing first, I'm trying to derive the equations that will be used in solid mechanics. Solid mechanics, you assume the object would be non moving, no? Just subjected to forces. So in that case, it's just like you do in statics or solid mechanics. What is the equation used all the time? Summation of forces equal to 0, no? Okay, exactly the same thing we are doing. So if we substitute over here, we end up with what? So substituting into above equation. So substituting in above equation, what do we get? We're going to get integral of the surface. Instead of Ti, we're going to get sigma ij and j. Can put the hat or no hat. ds plus the integral of the volume rho b sub I dv will be equal to 0. Okay? This is not over, okay? So now we have a surface integral and a volume integral. So they're not easy to work with because you cannot add them together. We need to combine, we need to have either two surface integrals or two volume integrals. Okay? So we can use the divergence theorem to make the surface integral a volume. Okay? So we're going to say using the divergence theorem, which is what? One going through a surface of T, let's say N ds. I simplify a bit the notation. This should be equal to the volume integral of the gradient of the del operator over the dv. Or we can just rewrite this in initial notation. T sub I, j, n of, why do I have a different index here? Let me just put this one as sigma right away. Sigma ij, because we can substitute it. N of j ds. So this is okay, and this one you can rewrite it as in functional volume as the partial of sigma ij delta xj dv. So since we're going to go to a different page, maybe let me just call this one A and this one letter I. And now the only thing I'm going to do, I'm going to substitute this quantity here into here, okay, into the first term, okay? So let me go to the next page. So substituting Roman 1 into A what do we have? We're gonna have that okay, so we're gonna have that so I just rewrite it. Let me just rewrite this equation, that way I don't do any substitutions one page to the other. So this is the initial equation here, the S plus integral of volume rho bi dv equals 0. So what you're gonna get over here is integral of volume of partial sigma ij partial x j dv plus integral of volume rho bi dv equal to 0. So now that both are volume integrals, we can combine them. So we get what? Partial of xij partial xj plus rho b sub I dv equal to 0. Okay, so above equation is satisfied when whatever term in brackets will be equal to 0, no? because it needs to be equal to 0. So you have partial xij partial xj plus rho b sub I will be equal to 0. Or you could write, this one as what? Sigma ij comma j plus rho b sub I equal to 0. Or if you want to use the more traditional notation, will be equal to the del of the gradient plus rho b of the body forces will be equal to 0. So anyway, you can use either from you want. Personally, I think I will use the first one. Okay, so remember over here, rho bi will be the body forces. And this term over here will be equivalent to what? To the what is the action of the external forces? Okay, because these equations here are equivalent to what? All these three equations are equivalent to what? I mean, we just said this is equivalent to summation of forces equal to 0, no? But now, let me ask you something, because this is important from the understanding point of view. Is that when you write down any Newton's equation, summation of forces equal to 0, what forces are we talking about here? You have two types of forces, external and internal. Obviously, I'm giving you the answer, no? But this one refers to external forces. Because what happened to the internal forces? What is Newton's third principle? Action, reaction, no? Same magnitude, opposite direction, no? So everything that happens within the structure, there is forces inside the structure, but if one is pulling, the other one is pushing with the same magnitude, but the opposite direction. So all the internal forces end up being 0. So what do you do every single time you need to derive the equation of something internal? What do you do every single time in engineering? How do you make those internal forces to become external so that you can use Newton's equation? You break the solid, you make a cut, no? Yeah? So by making a cut, you expose internal forces, they become external. Now you can apply Newton's equations. Okay? So when you say these forces, this is the effect of all the external forces that you can rewrite in function of the stresses. But this is really the external forces. Okay? All right? All right, so we got one equation for the translation. So this is equivalent to summation of forces translation. Okay? So now part B. We're going to look at the rotation. Okay, so the same thing for the rotation. I'm going to give really there is no summation of moments equal to 0. Newton's equation is just summation of forces. The moment equation is a consequence of the summation of forces. Okay, so I'm going to give the more general definition. So the rotational motion is defined by the moment created by the summation of forces terms So by the forces about an arbitrary point. Okay, so in other words, what do we have? We have summation of forces. So we have, okay, let me just put the moments right away. Summation of moments is equal to what? Is the moment created by these external forces. And what did we say was the definition of the summation of forces? Was equal to the linear momentum, okay? So we have rho cross MV. Yeah, okay? And now what is really this equation? What is really the meaning of this equation? What's the meaning of, what is the real name of this equation? This is the angular momentum equation. Okay, so if you think about it, what is the angular momentum? The example I generally gives when I teach dynamics is that this is translational velocity, but think about this one about just being rotational velocity. Okay, we're talking about rotation, no? So what happened to the figure I skated? You see ice skater goes, sometimes they start spinning, they open their arms. What happened to the velocity of the spinning? It goes slower, no? Because if you want, the angular momentum is a constant. If you open your arms, you increase R, so you need to reduce the spinning velocity. What happens if they start closing their arms? The spinning velocity increases, no? Because the R decreases and the spinning velocity, in order to keep it constant, needs to increase, okay? That is what the principle of angular momentum is all about, okay? So as before, we're gonna simplify the question. So we're gonna simplify the problem. So let us assume a static solution. Okay, which basically means summation of the moments equal to R cross summation of forces equal to R cross MV equal to 0. Or I can just say here that R cross summation of forces will be equal to 0. All right, so now is when we're gonna need our initial notation. So recalling the initial notation for a cross product so let's see, maybe let me go back to the black and consider this thinner. A cross B is equal to what? It's equal to A, let's say sub I, E of I, cross B of J, E of J, correct? So now this is equal to what? Epsilon ijk of A sub I, B sub J, and you take E sub I cross E of J, gives a perpendicular vector to both of them that we call E of K. Okay? So now, and from, I'm going to start simplifying a bit, and from page, let's see what would be the page over here. So let's see, and let me look at the page, let me write down the equation, then I look at the page. We know that summation of forces as is equal to the external forces is equal to, all right, so the summation of forces equal to 0. So basically from page 84, the summation of forces equal to 0, I can go and pick any one of these equations. Okay? So let me see and go and pick up this one over here. We'll give on the surface. So let me write this one first, then I can select which one to take. Rho B sub I. Okay, so I'm gonna go to the initial one, really is, okay. It's now page 84. I'm going back to, yeah, I can go to page 84, but I'm gonna go to this expression here. So page 84 top, that gives you sigma ij and j ds. As you can see, this is going to become now cumbersome. So, and this one, and what is R? Really, R is the position vector, so x1, x2, x3, or you could say this is just x sub I, no? This is the position vector. Okay, so we know this is the expression for A cross B. What I'm trying to do now is R cross summation of forces. So R will be x of I, and this will be the summation of forces. Okay, or this term over here. Okay, so that R cross summation of forces will become what? Summation of surface of epsilon ijk xj. All right, so let me hold on one second. I need to go back because of the notation. T sub I of n ds. I'm going to go back for a second to the other page in a second. Plus epsilon ijk xj rho b sub I dv and v. All right, previous page. I'm doing stuff backwards now. This is the definition of the Cauchy stress tensor. Okay. Maybe I should clean up a little bit my notes next time I do this section here to be a bit more consistent. Okay, maybe I should have done it a bit faster, but I just started the division as before. So as previously, using the divergence theorem. Yeah, I should clean up a little bit my notes. Which will be what? This term over here, epsilon ijk xj t of I and ds would become a volume integral epsilon ijk of partial, I need to use a new index x of q of xj t of I. Okay, I'm going to start simplifying a bit the notation, okay? This is being too much. dv I know notation here is becoming crazy because of the indexes, and from Cauchy's stress tensor or tensor, you're gonna have that so yeah, be careful here. You see, this is T of Q now. So T of Q will be sigma KQ and Q. All right, so and okay, so the equation star, I'm going to stop doing this stuff, becomes at the end, the derivation is not that important. Is the final result, the final consequence that's important, becomes integral of volume of epsilon ijk partial of xj sigma kq divided by the partial of xq plus dv plus the integral of v of epsilon ijk x of j rho bq dv, and this should be equal to 0, so I put it here. Let me finish the line and then you can ask me. And here now we just combine both of them. Epsilon ijk of partial of xj sigma kq over xq plus epsilon ijk, this one should stay unchanged, x of j rho b of q dV or 0 equal to volume epsilon ijk of partial xj partial xq sigma kq plus, so I'm doing the double products, xj partial of kq xq plus xj rho b sub I dv. Okay, so now I'm also going to use the notation. Wait, I'll do it at the end. That should not matter. So now what's going to happen is that we can write this as 0 equal volume epsilon ijk. I'm not recording? I think I am recording.
Yeah, you're recording.
I think when it's the green stuff all around, it's not recording. See if I do this now. That's absolutely fine. Okay, so we have this. And now what I'm gonna have, I'm still gonna have this term over here. Okay, let me see what I'm trying to find here. Is I'm gonna have, all right, so this one here, del xj xq sigma kq plus xj factor of partial sigma kq partial xq plus rho b sub I, and all these will be dv. Okay, but what did we just show for static? That this term is equal to 0. Okay, the summation force is equal to 0, and this term index is different, but it's the same as this equation here. Okay, so all this term over here is 0. If you want, from page, on my notes would be page 84. Okay, so at the end, what do we have? We're gonna have on the volume epsilon ijk of partial of xj partial xq partial kq dv will be equal to 0. Okay, now I'm not going to go into the details again, but if you remember, what is the definition of this? This is the definition of delta JQ. Okay, we could write the same thing. So above equation is satisfied if partial ijk partial jq sigma kq equal to 0. Okay, so for this equation to be valid, what needs to happen? K equal J, no? So let's say for Q equal J, the equation will simplify to epsilon ijk sigma kj equal to 0. So I know it's not been fun lately, huh, the classes with all this stuff. When it was only initial notation, it was more fun, but now. So what is it? So this equation is equivalent to what? This is equivalent to summation of moments equal to R cross F equal to 0, no? But that doesn't look alike at all, no? All right. However, this one has a good implication. That's why I did all this derivation, is just to go to the conclusions now that we're gonna show. Okay. Okay. So now let me do some calculations over here. So let's say for I equal to 1, kj equal to 3. So what we're gonna have epsilon 1, 2, 3 sigma 3, 2, okay, plus epsilon 1, 3, 2 sigma 2, 3 equal to 0. So now we know that epsilon 1, 2, 3 will be positive 1, so it will be sigma 3, 2, but 1, 3, 2 will be negative, so it will be minus sigma 2, 3 equal to 0, and this will imply what? That sigma 2, 3 equal to sigma 3, 2. Okay, now we could do the same thing, but so let's do it for I equal to and kj equal 1, 3. Oh, we do 2 times. Maybe you know what I want to get. Okay, so what are you gonna get? You're gonna get sigma. So let's see, 2, 1, 3 epsilon. What would be 3, 1? No, jk, yeah, 3, 1 plus epsilon 2, 3, 1 epsilon 1, 3 equal to 0. So basically is, oh wait, I put the same thing here. No, 2, 3, 1. So 2, 1, 3. This one should be then negative. This time I change it, so it should be minus 3, 1 plus sigma 1, 3 equal to 0. But again, this will mean what? Sigma 1, 3 equal to sigma 3, 1. And then what we have for I equal 3, kj equal 1, 2, what are we going to get? So sigma 3, 1, 2, sigma to 1 plus epsilon 3 to 1 sigma 1, 2 will be equal to 0. So this gives you minus sigma to 1 plus sigma 1, 2 equal to 0, which means sigma 1, 2 equal to sigma to 1. So what does that imply? What is the implication of that? Is that if we want our body to only have translation and not rotation, the stress tensor or the stress matrix needs to be what? Needs to be symmetric. Okay, and that's why. So if the stress matrix is symmetric, what is that implying? Is that we are not considering any rotational motion. Okay, that's really the implication of having a symmetric stress matrix. Okay, or stress tensor. Okay, so let's just write it down. So above results implies that okay, let me put it this way, that if the stress, let me say matrix slash tensor is symmetric, no rotational motion is being considered. So if the matrix is symmetric, we are only studying basically translation. Okay? And basically, if it's only translation, what is the implication? What is the major implication? Is that you're saying that bending stresses will be dominant and really you will not be looking much at the shear stresses, no? Okay? So the deviation was maybe long and a little bit tedious, but the consequence at the end, the result is extremely important, no? From this. Is that what is really the physical meaning of having a symmetric matrix or stress tensor is that you are neglecting the rotational motion of that object. You are just considering that object to move in translation. Okay? And there is not being rotation. All right. All right, so now let's just do a very simple application, a consequence of this, which basically is to do the derivation from, I don't know if we have time, but we can start it. Basic derivation from solid mechanics, but basically following the same thing that we did. We did all this stuff is 3D, no? With the IJ case and some indexes. Let's try to simplify it to a 2D problem and see what would be the equation. So all this is very complicated. That's the problem of the integral notation. It's so general that it's hard to follow or to have a good picture of what is going on. So let's say example here. We're going to simplify a lot. So you need to derive the equilibrium equation for the beam shown below. Okay, so this is any solid mechanics textbook has this derivation, but now you should know how to do it. So let's say we have a simply supported beam. So let's see, why am I doing the boundary condition this way? Why do I put a triangle here and just a circle here? There's a mathematical reason. What is the total number of unknowns we can have on a static problem? 2D. 2D. 3. So this includes 2, and this one just 1, no? If you really put another triangle here, you're implying 4, no? And there's not enough equations. So it should be what is called an overdetermined problem, no? Okay? So now we're going to assume here a distributed load, a uniform load, sorry. It's distributed, but it's distributed uniformly of intensity Q of X. This is the notation generally used in textbooks. And again, let's say this is Y and this is X. So, in order to define the equilibrium of this equation, we know that the only equation we can use is summation of forces equal to 0, whatever you want. But we want to see what is happening inside the beam. So we want to know what's happening inside the beam. What do we need to do? We need to make a cut, no? So let's say we make cuts here. Let's say we make a cut here and a cut here. So we cut it. And now we're going to have this piece over here. We're still going to have the distributed load. Q of X. But now what's going to happen? You're going to have, this is going to create some type of moment, no? Whatever you want to do it. So generally you would do this. You can do reverse, but let's say it will be some shear force here, V1. Some shear force here, V2. Why are these two in opposite direction? Because it should be equal to 0, no? At the end, you still need to be able to apply summation of forces equal to 0. All right? And now, the same thing for the moments. If you have a moment here going clockwise, you need to have a moment going on the other side counterclockwise. Because again, this needs to be in equilibrium. All right? This object does not need to be moving. Okay? So here we know that V is shear force and M would be bending moment. Okay, so if we assume only translation, what is the equation we're going to use? Summation of forces equal to 0. Okay, in this case, if you want, what would be the direction? Let's say I choose on the Y direction, no? If you want, just put summation of forces on the Y, it would be easier. So if I do only that on the Y, what do you get? You get minus V1 plus V2 minus, this is a distributed load, so you want to find the value, will be Qx dx. And to call this one, let's say between x1 and x2, okay? But you don't need to put that. All right? And this should be equal to 0. All right, let me just rewrite this a little bit differently. So this will be really, if I move this one first, this will be V at x2. This is really V2 minus V at x1. This is really V1 minus integral of Qx dx between x1 and x2 equal to 0. Okay, so really, what is this term over here? Is dv, no? Okay, so what I can do now is I can divide by this length of elements, and I will get what? This will give you. This term over here will be dv dx integrated between x1 and x2. So I'm integrating this term, all right? dx will disappear, will be dv, okay, for integration. And this should be equal minus integral of x1, x2, q of x dx equal to 0. Why am I doing this over here? You see, as before, we had a surface integral and a volume integral. Now we have a constant to a one-dimensional integral. I'm transforming the constant to one-dimensional integral, no? This one. Why do I do that? So I can combine both integral signs. So now from here you get that here you're going to get integral x1, x2 of dv dx minus q of x dx equal to 0. So above equation is satisfied if dv dx minus q sub x equal to 0, or what is generally what they give you in solid mechanics or even statics, is that the distributed load is equal to dv dx. And generally, generally you have q. Generally, q of x is given to you, no? So how do you find the shear? You need to integrate this. So the shear would be the integral of qx dx, no? Yeah, for the shear. So you want here generally qx is given such that the shear force so we have dv equal to qx dx, no? Or you will have here, if you want, v will be equal to the integral of qx dx. So this is just for the summation of forces. Now we can do something different for the summation of moments. But what is the result? I mean, I don't know if you remember, is that you have this one would be qx dx, and then what would you have about the shear? And the shear will be in function of the moment. And that's why when you were doing the shear bending moment diagram, if you had a straight line for the shear, what was the distribution of the moment? It was like parabolic, no? I mean, you have to derive. But you see, all this stuff comes from what we just derived. Same procedure, but limited for 2D. Okay? So next time, we don't have time, we do the moment equation and we keep going. All right?